Hi, I hope you can hear me. So this is the first review session for CMSC 351 algorithms. I'm Gihan, I'm a TA for this course. This is not the recording of the live session that happened on 1st September of 2021. I'm recording it again for the benefit of the students who didn't show up for the review session. There will be a little bit of difference between this recording and what was done in the live session, but I hope they will be more or less equal. Yep. So today's topic is time complexity, and this is one of the most fundamental problems when it comes to algorithms, and we are going to talk about two things in particular. One is big O, that is the recurring topic in this main topic. So you always come up with problems to solve for big O, find big O, prove big O is this, big O is that, all that. And then there are some other things which are also coming under time complexity, which we will discuss in this review session. So so the first question is, why do we need time complexity for programs? So think of a situation where you have find the program runtime for some algorithm. So you have an algorithm, you write the code and you run it on the computer. I'm going to think about two algorithms here. One is bubble sort, which is the blue line here, and also we have the merge sort, which is the red line. So what's going to happen is we're going to run the computer program on different. So sorting happens on arrays. Let's say the array size is n, the input size is n, and the time taken for the program to run is tn. So we are going to experimentally run this on array sizes 100, 200, 300, up to 500, and measure the time and plot it. So you will see this trend lines for the runtime. That's all fine. That is something you can easily do, an experimental thing. We do that, and so we can do that easily. Get rid of that, and so the problem is what is the tn for a particular input size n to do experimentally, but there is a small problem. Even let's say we are just focusing on bubble sort in the second graph, we are going to run it on 3 computers. One computer with a 2 gigahertz processor, 3 gigahertz processor, and another computer with a little amount of RAM. So let's say the first two things have equal amount of RAM, which is a higher amount of RAM, and the third computer has a small amount of RAM. You will see that the time taken for this program to work on inputs of different n is not the same, even for the same algorithm in different computers. The problem is experimental measures are highly susceptible to different experimental setups. The computer, maybe the programming language, compile, operating system, and everything. So experiments are not good enough to give a general answer. That is where the problem begins, and how are we going to solve it? For that, we have theoretical analysis for the runtime. But the problem with using the word runtime is whether we are actually measuring time in seconds. So these two graphs, since this graph and this graph, since we did it experimentally, we can always have the y-axis in time seconds or milliseconds. But when we do the theoretical analysis, even though we call it runtime, it might not be the time at all times. Can I hide the meeting control? Yep, then we are going to do it using something else. We're going to think of an ideal computer which can do a particular set of operations, unit operations, on equal amount of time, a unit time. A unit operation can be done in unit of time. So if you can do that, then you can find the number of operations will be directly proportional to the time. So you can say we do this many operations, that means it takes this much time. the obvious shortcoming of this is that there is no such ideal computer and not every operation run in equal time, but let's assume that there is for the sake of this section of the course. So when we are going forward, we need to this is not directly present in the course material, but you need to understand what these two words means. So what is a weak statement and a strong statement? We'll be using that over and over in the next few minutes. I'll just tell you 3 examples. I'm going to make a statement. Everyone in this class is at least 2 feet tall. That's statement A. Then I'm going to say everyone in this class is at least 3 feet tall. That is statement B. And then I'm going to say everyone in this class is more than 3 feet tall. Okay. If you look at the first 2 statements, everyone is taller than 2, everyone is taller than 3. Which of these are a strong statement? For example, you can say the first statement for a lot of classes, even when there are people with 2.5 feet, 2 3/4 feet tall in the class, or maybe even 2 feet. But you can't say the second statement for all those classes. So the statement B is more restrictive. That is why we call that a stronger mathematical statement. So A is weak compared to B, and B is strong compared to A. And if you look at B and C, do we get the same idea? Let's try to what's that? Okay. What about, so I'll show you this picture to say how what a weak statement and a strong statement is. So think of it this way. A, B, and C are sets that are defined by these statements. For example, these sets, the elements of these sets are different classes. There can be many classes inside A. So you have many classes inside A. Some of these classes might be inside B. For example, if there is a class which all the students taller than 3 feet or 3.5 feet, it will be inside B. And it will also be inside A. So using both those things, you can say there are statements which are in A but not in B. But there are all the statements in B are in A. So weaker statements make broader classes or sets because it's easier to get into A than to get into B. And C, it says everyone in the class is more than 3 feet tall. So why is C stronger than B? Because in order for something to qualify to C, you cannot have people of 3 feet as well. So for example, there is an area here which is in B but not in C. This area, all the classes with people of height 3 and above are in this area, but only the classes with all the people taller than 3 feet can go into C. Now you see why you have weaker statements and stronger statements. We'll be using this over and over. Moving on, let's come back to complexity. When we are talking about complexity, we are talking about functions of natural numbers, projecting those natural numbers to natural numbers. What are natural numbers? They are numbers such as 0, 1, 2, 3 up to infinity. Some definitions say that natural number starts only from 1. Either one of them is fine for our course, but some definitions say only counting numbers start from 1 and natural numbers start from 0. That doesn't change a lot of things for us, but however, let's talk about two functions which takes the input from the natural number set and outputs a natural number. Now, if we think about our previous function, which was Tn, it takes in simple n as the input, which is the size of the input. For example, if it's about arrays, it's the size of the array. Maybe it can be about bits. Again, bits are also in the sizes 0, 1, 2, 1, 2, 3, 4. So, and it is outputting a natural number because we are talking about unit operations or units of time. We said that I talking about this ideal computer which can do this. So Tn is also a function which starts from natural numbers and goes to natural numbers. So f and g are both matches for Tn. What we can say about time complexity using these functions is, if we have this condition, so this is the condition for big O, big O. So we can say Fn is big O of Gn. Fn is big O of Gn. This is how we write it. If there exists a C and a N naught, there are two things here, a C and an N naught, such that for all n bigger than N naught, you have this condition. You have to have Fn and you have to have a Gn. So you're going to say Fn is big O Gn when you have these two. You can find these two numbers basically. If there is an N naught after which all n bigger than or equal to N naught, you have this condition, which can also be said as a upper bound for Fn, because to say Cgn is always larger than or equal to Fn, because of that Cgn is an upper bound of Fn, and that's when you say Fn is big O Gn. So that's even though we have an equal mark, equal sign, that's what we say. And C has to be a positive real number and n has to be a natural number. Why? Actually, n naught has to be a natural number. Why should n not be a natural number? It's because n naught is again one of these n numbers given by n. N after n naught is showing this property. So n naught should also, because n is here in this natural number set, so n naught should also be in that natural number set. So we have these conditions and we have this condition. That is what big O is. With that, we'll go into a graphical representation of what big O of Fn is. So we have Fn here, and after a particular n, so this area is n is larger than or equal to n naught. You can see the n naught here. So after this point, from this point, since you have this equal mark as well, from this point onward, Cgn is always larger than Fn. So you can see Cgn is an upper bound for Fn for all n. So you can see that. So this is what big O is. So this you can say as Fn is big O of Gn. That is big O notation and what it means. With that, we will go to why do we have a C? So can't we do this with just a Gn? Because we need to find an upper bound, isn't it? Isn't it enough if we just show a Gn upper bound? The problem is how we like to keep things. For example, think about these two functions. We have an f1 and f2. Both these functions look the same, look more or less the same, but they have they are a constant multiple of each other. For example, f2 can be around 1.5 times f1 or 2 times f1 something. So we can say f2 equals k times f1. This is an intuitive explanation. It shouldn't always be a constant time, but if we say that these are two functions of same shape but different height, so constant multiple, the thing is we would like to have a equal of, like if we can say if you can say different upper bounds for these two, it's fine, but we would rather have we would rather have the same upper bound for both these functions. But as you can see, since they have the same shape, you can have the same function and you can have the same function and scale. You can have the same function g n, and you can scale it such that it will be an upper bound for both these functions after particular n nodes. For example, with C1, you can create the upper bound in this region for F1 node. And you can, with C2, you can create the upper bound by C2gn in this region. So you can see for similar shaped functions, you can have the similar upper bound if you use this constant factor. It is easier to express ideas when you have that. So similar shapes, we would like to give, it's just arbitrary. We would like to do that. That's why we put in a constant. Anyway, it's more meaningful to talk about functions that way. And why do we think only about n is bigger than n naught? You can see these upper bounds are upper bounds only after particular n naught. That is because when we talk about computational complexity, we are actually worried about how runtime grows with larger input sizes. Because for smaller input sizes, you can always make them work somehow. Because computers are powerful, you can, for like smaller inputs, most of the functions, you can make them work. But when they have to work on very large inputs, that's when the problem comes, and that's what we are worried about, whether algorithms will slow down dramatically for very large inputs. So for example, even in this case, even though we have no idea about the upper bound or the lower bound in the region before n naught, or for this upper bound in this region, we know that upper bound holds after a particular level. So that is what is meaningful. If we know how it, because smaller things like anyway, you know this thing, right? If n naught is any small, some time, like let's say this time, let's say this is t naught. T naught is enough for the program to run anyway. What we are worried about is larger inputs, because t naught might be a very small time limit. You can get the thing done, but you are not worried about that. And also another important thing is, even though we have two constants here, you can see after a particular n, which is n naught 2 here, both these upper bounds hold after that. So that is an important thing as well. Even you have all these complications for smaller numbers, after a particular number, these upper bounds hold. That is the important thing, because we are worried about larger input sizes. With that, we'll go to some other definitions other than big O. They are, so we have f and g functions mapping natural numbers to natural numbers, and we have c's, positive reals. So the idea is we have different definitions here, and we'll be using different c's here. That's why we have a ci, and we'll be using different n's. We have nj, and all n is in natural numbers, and this is also in natural numbers. That goes without saying. So we talked about, first we talked about big O, big omega and big theta. So we know what big O is. Big omega is the same thing, but the other inequality. So when Fn is less than, sorry, just give me a moment. When Fn is larger than or equal to C2gn, we say it is big theta of gn. So C2gn is a lower bound for Fn. This was the upper bound, and this is the lower bound. And then we have another definition called big theta, which is if Fn is big O gn and Fn is big omega gn, which means you have the upper bound with gn as well as the lower bound with gn. It should be gn here. This is Gn. So if you have the upper bound and the lower bound, then you say it's big theta. We'll look why this is important as well. So if you have an upper bound, so the idea is if you have a function, you know the upper bound and the lower bound, you know more information about the function. And let's go into some other definitions, which are small o and small omega. So how we define small o is when the limit, when n goes to infinity, of fn over gn goes to 0, fn is small o gn. And when limit n goes to infinity, gn over fn is going to 0, fn is small omega gn. You can convert this and write it in another way. That is, if fn is smaller than gn, it is small omega gn. If fn is larger than n, fn is larger than gn, if it is fn is small omega gn, and these limits should hold when n goes to infinity. Yeah, so this is small omega. One of the important things to see here is you didn't have the equal sign here. Earlier we had the equal sign in big O and big omega. So in small omega and small o, we don't have the equal sign. That's an important point. And we talked about stronger conditions or stronger statements and weaker statements. So I'll just look into two statements here. Let me talk about this. Here we have a statement here and another statement here. Which of these are the stronger one? This is stronger than this. It is because for some function to qualify for the inequality alone, greater than or smaller than, so these things, it is difficult to qualify for that compared to qualifying to the conditions where you have a greater than or equal or a smaller than or equal. That is because even something that's equal can be here, but something should be definitely larger than to be here and should be definitely smaller than to be here. So yeah, I wanted to say that. So important points, small omega and small o are stronger statements. Because of that, if you have small o, it implies big O. And if you have small omega, it implies big omega. But it doesn't happen the other way. Because you can go from the stronger statement to the weaker statement. Stronger statement always implies the weaker statement, but the weaker statement does not imply the stronger statement. And another thing we have to learn is how to rigorously prove big O and big omega. So if you have to show that something is big O of that, you have to, if you can, there are like easy ways of sure, just writing the answer saying this is the biggest, highest order term and whatnot. But if you want to rigorously means like prove, actually mathematically prove, there are two approaches. The first approach is you obviously have f and g. You have f and g, you are going to prove something with that. So start with an arbitrary c and an n naught and show this condition will hold for all n is bigger than n naught. So you arbitrarily pick a c and an n naught and then show this condition for n is bigger than n naught. That is the approach one. Of course, you can go it in the other way as well. The other way would be assume this is true. Cgn is larger than or equal to fn, and then for all n, you're going to assume the whole thing, and then show that at least one C and one N not exist. So show this, and if you can solve this and show there is a particular value for N naught and a particular value for C, that is enough. All you have to show is at least one value each for C and N naught. That's enough. However, sometimes you may even be able to prove that there are multiple values for C and N. Or maybe you can even show there are infinitely many values for C and N. Both of those things are correct, because if you show any of these two conditions, you are already showing there is at least one, because if there are multiple, there is one. Okay. Then we'll go to how to rigorously prove big theta. How you do that is you first rigorously show that how you do that is you rigorously show Fn is big O of Gn, and then you show Fn is big omega of Gn. Then this will automatically imply Fn is big theta of Gn. So the idea is you have to rigorously prove these two things if you want to rigorously prove the other. I'm sorry, I'm not really good at this tool. This is my first time doing this. I'll probably get better with time. Rigorously prove this, and it will imply. Yeah, it will imply the big theta. That's easy. Okay. And what do both these things actually mean? So say you have this function fn, you need to understand how it behaves for very large inputs. Because of that, you find an upper bound with G2, and you say that the upper bound is valid after this value, after this n naught. And not 2, I say n naught 2 because it's the upper bound, and I'm also showing a lower bound after this. So you know after a particular point in n up to infinity, fn's behavior can be limited by these two functions. It's a meaningful thing. For example, like let's go back to the earlier example I was talking about, people in the class for something. So if you can prove at least you don't know everything about like people in a very large class, but you know everyone is taller than 3 feet and everyone is shorter than 10 feet. Even that is enough, because that is meaningful. So we use these upper bounds and lower bounds to talk about the asymptotic behavior, which is how functions behave in the infinity. That is it. So thanks for listening. And I think we did 1 or 2 examples about showing these things rigorously in the live review session. I'll just go through everything fast. So this is the first review session. We talked about complexity, why we need complexity, why experimental things are not always enough. Then we went to what runtime is and why it's not measured in seconds per se, why we have that in units. And then we just looked into what weak and strong statements are. And then we talked about what big O is, and we understood it through this graphical representation. And then we talked about why we have a C constant here. And then we talked about why we can talk only about n is bigger than n naught. Then we talked about other definitions such as big O, big omega, big theta, small o, small omega. And then we talked about which of these are stronger statements and which of them are weaker statements. And then we talked about how to rigorously prove these things, all 3 things, and even another 2 you can rigorously prove some in the similar manner. And then what do these things actually be? So that's it. Thanks for listening. And if you have any more questions, you can come to the TA hours.